So in this video, I will explain how to solve an LPP problem. So we're going to maximize a profit function, which is given here. Z is equal to 5x1 plus 3x2. So we are going to deal with this LPP problem using the algorithm. It's called a Simplex algorithm. The algorithm is very simple, but it contains several steps that you have to implement in a particular order so that the algorithm will work. So what we are going to do is we're going to maximize the function which is given here, z is equal to 5x1 plus 3x2. So this is the cost function. X1 and x2 typically represent the so-called decision variables. So x1 and x2, they represent the decision variables. So we are going to maximize this function subject to some constraints. The first constraint is x1 plus x2 is less than or equal to 2. 5x1 plus 2x2 less than or equal to 10. This is the second constraint. The third constraint is 3x1 plus 8x2 is less than or equal to 2. So this is a typical chemical engineering problem converted into an LPP problem. So the actual chemical engineering problem will look something like this. So this is something related to a production planning in a chemical plant. So maybe I will make a separate video on how to convert this chemical engineering problem into an LPP problem. So that will look something like this one. So what we did is we took this whole chemical engineering problem, we wrote the cost function, and then we also developed a few linear inequalities. They are nothing but some constraints involved in the actual problem. Yeah? So we don't have to go into the details of this whole chemical engineering problems. What we are going to do is just we will assume that we already converted the chemical engineering problem into an LPP problem. So which means LPP problem should contains typically a cost function and then several linear inequalities which are nothing but constraints. So we will solve this problem using a algorithm which is called as a simplex algorithm. So how the simplex algorithm looks like. So this is something I created on my own. I mean, like, it's not my algorithm, but I just presented the algorithm in different steps. Yeah? So I have roughly 9 steps. So you have to execute all these 9 steps in series. Yes, you have to execute step 1, step 2, step 3, step 4, and you have to reach until step 9 in order to complete the algorithm. Yeah? So we will use this simplex algorithm. So and we also learn this simplex algorithm by solving this LPP problem. Yeah? So it is best to learn this algorithm only through solving the problem. If you know how to solve the problem, then it's really easy to learn the theory behind the simplex algorithm. Yeah? So let's solve the problem using the simplex algorithm. So as I said before, you have a cost function and you have a subject to several constraints. So how to implement the simplex algorithm? Yeah? So let's read my version. So the very first step that you need to do is ensure all the right hand side are non-negative. Yeah? So this means all the linear inequalities that should be a positive quantities. Yeah? So let's see that. So you have some constraints, set of constraints here. x1 plus x2, second constraint, third constraint. And then you also have some linear, how do you call, some non-negativity constraint. Yeah. So to implement a simplex algorithm, normally we ignore this non-negativity constraint. We will take only all the linear inequalities, and then we have to make sure the right hand side is positive quantity. So you see here is 2, you see here 10, you have something 12. So all are positive quantities. So which mean, so this ticks the box. Yeah, we can tick this box. So ensure all the right hand side values are non-negative. Is this true? Yes, this is true. So which means step 1 is complete. So what we did is ensure, or we can say all the RHS values are positive. So the first step is complete. And then also you have to make sure, so if any of the right hand side is negative, so we will multiply the entire constraint by -1 so that the right hand side will be a positive quantity. So this is a must rule. So that's step 1 in the simplex algorithm. So this is something we completed already. So what we are going to do now is just to maximize the function. For minimization, the procedures are same, but there are a few things that we have to change, but that we will cover in a separate video, that we will learn in separate video. Yeah? So let's solve this. And then the second variable, the second step in the simplex algorithm is you have to convert all the constraints into inequalities. So it means you have to take all the linear inequalities and then you have to convert them into inequalities by adding something called as slack variable. Yeah, so you need to add slack variable in order to convert the inequality symbol into equality. So that's the second step. So what do we mean by that? So if you have something like this is the linear inequality, isn't it? X plus x2 is less than or equal to, because it has an inequality sign which is less than or equal to 2. So we have to convert this into linear equation by adding a slack variable. In this case, I put the value s1. S1 is nothing but a slack variable. So slack variable, what do we mean by that? So these are some unused resource, yeah? So which we never use and that will not impact your profit. So which means slack variables are nothing but unused resources. Yeah? So but we need this, we have to include them in order to execute this algorithm. Yeah? So let's do the second step. We are going to convert all the inequalities into equalities by adding a slack variable. Yeah, for the simplex algorithm, all we need to take is these ones, yeah, not the non-negativity constraints. So let's take the first linear inequality and then convert it into a linear equality, linear equation. Sorry, yeah. So x1 plus x2, and let's add a slack variable x3. That's equal to 2. So we converted the linear inequality into a linear equation by adding a slack variable x3. So we do the same for the second linear inequality, 5x1 plus 2x2 plus x4, that's equal to 10. So again we converted the linear inequality into a linear equation by adding a slack variable, this time x4. So take the third linear inequality and then convert them into linear equation by adding another slack variable. So 3x1 plus 8x2 plus x5, so that's equal to 12. So what we did is we converted all the linear inequalities into linear equation by adding a slack variable. So we have 3 linear inequalities, so we have 3 slack variables. So now we have to rewrite. This is only for convenience, this step. Yeah? So now rewrite all these equations so that all these linear equations will contain all the slack variables. Okay, so how do you do that? So let's see. x1 plus x2 plus x3 plus 0x4 plus 0x5, that's equal to 2. So similarly write the second one, 5x1 plus 2x2. This time you don't have x3, so we put 0x3 plus x4 plus 0x5, that's equal to 2. Now take the third equation, this one, 3x1 plus 8x2 plus 0x3 plus 0x4 plus x5, that's equal to 12. Yeah, so we almost completed the step 2. So we converted all the linear inequations into linear equations by adding 3 slack variables. Yeah? So you have x3, x4 and x5. So all these quantities are nothing but your slack variables. Oh sorry, this should be equal to 10, not 2. So 5x1 plus 2x2, that's equal to 10, isn't it? Yeah? So this is 1x4 plus 0x5, that's equal to 10. Yes, so now we completed the second step. So now we go to the third step, which is write the objective function in terms of all the variables. Yeah, now, so which means we have to include now decision variable plus the slack variable. So decision variables are nothing but x1 and x2 in the profit function. And now we have 3 more slack variables, which is x3, x4 and x5. So we have to include them in the so-called cost function z. Yeah, z is a function of x1 and x2 is in it. Yeah? So now we have to add the slack variables. So let's write. So that's our profit function or cost function. So we have to write this function by including in terms of all the variables, which means, so that's the step 3 is in it. Yeah? So we have to include the decision variable and the slack variable. So how do you do that? It's very simple. So take this equation, which is your cost function. So step 3, z is equal to 5x1 plus 3x2. Now we are going to add the unused function, unused variables, which are nothing but your slack variables. 0x3 plus 0x4 plus 0x5. So that's equal to 0. Yeah, so sorry, that's equal to, yeah, not equal to 0. So that's all. That's your profit function. Sorry. So what we did is we took the cost function and then we write that cost function in terms of all the variables involved in the problem. So which is you have 2 decision variables and the remaining 3, which is slack variables. Sometimes we call the slack variables as basic variables. So we almost completed the step 3. So if you notice in step 3, you can see that all the slack variables or the basic variables and have a coefficient which is equal to 0. Yeah, so which means all the slack variables have coefficients of 0 in the objective function. This is sometimes it's called objective function. So these are some jargons in the LPP: objective function or cost function or profit function. Yep. So, so we finished step 3 in the simplex algorithm. Only a few more to go. So what's the next step? So let's put the procedure here. So set the initial simplex table. I don't know, they use this word tableau. I don't know what does that mean, but this is how you see it in some of the textbooks, optimization textbooks. Yeah? So we have to, the next step is to construct the initial simplex table. So we will use the simple language. So your table should contain few things. Remember that. Yeah. So these are the these are the things that you have to pay attention really carefully. Yeah. So column 1 should contain coefficients of the basic variables. Yeah, which mean the first table will contain the coefficients of the slack variables. I will first read and then I will write it. We will construct the table. So then you will understand what this mean, what all these lines mean. Yeah? So and column 2 should contains the basic variable themselves, which mean the slack variables. So these are the conditions for the first table, the very first simplex table that we are going to construct. And then column 3, this should contain the right hand side of the constraints. Okay, so which means the right hand side of the all the linear equations which we constructed from the linear inequalities. Okay, and then the remaining columns is just the coefficient of all the variables in each constraint. Okay, so let's do this. So let's build the table. So let's write first column. Let's begin with writing the column 1 and then column 2 and column 3. Yeah? I'm really struggling to explain this algorithm. Let's do that. So if you go back here, so we will make the table. So first column is the coefficients CB of the current basic variable. So let's put CB. Well, for the moment, let's call it as CB. Coefficients of the current basic variables. So what do we mean by that? Yes, okay, let's first write the column, the titles in the column. Yeah? So the basic variable themselves, XB, let's put that one here, XB. The next one, third column should be the right hand side of the constraints, yeah? Which is this one. Follow the pen, right hand side of the constraints. And then the remaining columns are nothing but the coefficients of all the variables in the each constraints. So what do we mean by that? So coefficient of the all the variables means, so we have 3 constraints here. So follow the pen here. We have three constraints, 1, 2, and 3. And then we have to write the coefficients of all the variables in the constraints. So which means that includes your decision variable and the slack variable. So for constraint 1, the coefficients are 1 with respect to x2, 1 with respect to x2, 1 with respect to x3, 0 with respect to x4, and 0 with respect to x5. So these are nothing but your coefficients. So write the coefficients. So that will go here. Yeah, that makes the remaining column in the simplex table. So let's put x1, x2, x3, x4, and x5. Okay. So we have 5 columns here. That's because we have 5 variables, including your slack variables. So x1 and x2 correspond to decision variable, x3, x4, and x5 correspond to the slack variable. So let's go back to the original problem. So what we need to fill here is CB. Oh, and one thing I forgot to write, which is your cost function. Write your cost function here that contains all the variables, so which is here 5x1 plus 3x2 plus all your slack variables. So I write it here. 5x1 plus 3x2, 0x3 plus 0x4 plus 0x5. So this is nothing but your cost function. So these first two columns that you are seeing here, so these two corresponds to your cost function. Okay, and all the other columns corresponds to these ones, they all corresponds to the constraints. So which are now nothing but some linear equations, because we converted those constraints which are typically linear inequalities, we converted them into linear equation by adding some slack variables. So what does this mean? Coefficient CB. Let's go back to our algorithm paper. Yeah? So coefficients of the current basic variables are initially the slack variables in the cost function. So what do I mean by that? So you have this. So on the xp corresponds to the basic variable themselves in the cost function. So what are the basic variables in the cost function? x3, x4, and x5. So write that x3, x4, and x5, and the corresponding coefficients is nothing but your CB. So that's what is written here. Coefficients of the current basic variables, initially the slack variables. I put the word initially because this is something, this rule apply when we are going to build the very first simplex table. So the coefficients of x3, x4, x5 in the cost function is 0, 0, and 0. 0, 0, and 0. Yeah. And what is the right hand side? So now the remaining column, everything corresponds to what? They all corresponds to the constraints. Yeah. So right hand side means they all correspond. So these are the constraints, no? So 1, 2, and 3, and these are the variables involved in the constraints. And the right hand side of all these constraints are 2, 10, and 12. So write that one, 2, 10, and 12. Yeah, so which means we have 3 constraints, and that's why we have 3 slack variables here in the cost function. And now we have to write the corresponding coefficients x1, x2, x3, x4, x5 in each of those constraints. Yeah, so for example, this is the constraint number 1. So the coefficient of x1 is 1, coefficient of x2 is 1, x3 is 1, x4 is 0, x5 is 0. So write that. So the coefficient of x1 is 1, x2 is 1, x3 is 1, x4 in the first constraint is 0, coefficient of x5 in the first constraint is 0. So similarly do the same for the second constraint. So 5 2 0 1 0, 5 2 0 1 0, and then here for the third constraint 3 8 0 0 1, 3 8 0 0 1. Yeah, so that we almost finished 50% of the simplex table. So we are doing a lot of things now. So you have to remember them, that all the steps. The algorithm is really simple, but you should know how to implement it. Yeah, you have to know how to implement the mathematics. So what we did now, so we're trying to make the table. So this is something called as the initial canonical table, and now we have to fill the table. So the next row is something called as a z suffix j. But the moment, let's put that one here. So let's put z suffix j here. I will explain what does this mean. And then, so z is already something related to your cost function, isn't it? Yeah? So z suffix j. And then the next one is something called as c. If we go back here, so you have to write something called as cj. Yeah, I will tell what does the cj mean. C suffix j. So both has to do something has to do with the cost function that we have. Yeah. So zj is what? Zj is the coefficients. Sorry, zj is the something that we have to calculate, and then I will tell what is zj is. So zj is something, it's a dot product of two vectors, so it's nothing but cb multiplied by the coefficients in the constraints, coefficients in the constraints. So this is very tricky, remember this. Yes, so cb, which is this column, multiplied by coefficients in the constraints, which mean this one, x1 x2 x3 x4. These are the constraints, isn't it? Yeah? And then the coefficients mean like coefficient of x1, coefficient of x2, coefficient of x3, x4, and x5. So we can write in a mathematical format. So cb multiplied by x of I, so which means cb multiplied by x1, cb multiplied by x2, cb multiplied by x3, and so on. Yeah. So zj, and this is cj. Okay. And the next one that you should write in this table is zj minus cj. Okay. So what is this cj? Cj is nothing but the coefficients of the variables in the cost function. Yeah? So remember that this is cost function, not in the constraints. So what do I mean by that? So coefficients of all the coefficients of the variables in the cost functions means, so your cost function is here, x1, x2, x3, x4, x5. So the corresponding coefficients are 5, 3, 0, 0, and 0. So let's write the coefficients here. So coefficients are 0, oh sorry, not 0, 5, 5, and then x2 is 3, coefficient of x3, x4, and x5 in the cost function is 0, 0, and 0. 0, 0, and 0. And zj is something I said, coefficient cb, isn't it? Yeah? Coefficient in the of the basic variables in the cost function multiplied by your variables, coefficients in the each variable. Yeah? So how do you do that? So zj is, you have to multiply cb multiplied by x1. So that's what you have to do here. Yeah? So how do you do that? So 0 multiplied by 2. So let me write that one here. So I'll do the calculation here so that you can easily understand. So we're going to multiply this column multiplied by this column, yeah. So which is 0 multiplied by 1 plus 0 multiplied by 5 plus 0 multiplied by 3. So that makes it 0, isn't it? Yeah? So which means Zj will be 0 with respect to variable x1. So now we have to calculate the Zj with respect to variable x2. So how do you get that? So multiply Cb multiplied by all the coefficients that corresponds to x2, yeah, in all the constraints. So that will be 0 multiplied by 1, 0 multiplied by 5 plus 0 multiplied by 8. Oh, sorry, 0 multiplied by 2, this one, plus 0 multiplied by 8. It makes it 0. So here it will be 0. And now do the same. 0 multiplied by 1 plus 0 multiplied by 0 plus 0 multiplied by 0. So that will make it 0. And similarly, 0 multiplied by 0, 0 multiplied by 1 in x4 plus 0 multiplied by 0 in x4. That makes it 0. And similarly, you will get 0 here. So you already calculated Zj. And now we calculate, you know what is your coefficients of all the variables in the cost function which we entered here. So now we have to calculate Zj minus Cj, which is 0 minus 5, that makes it minus 5, 0 minus 3, that makes it minus 3, this makes it 0, 0 and 0. We almost completed the initial simplex table, and then so this from now you have a lot of tricky business to do. So until now everything looks easy. All we did is some arranging the table, putting everything in the right order, and we did some basic multiplication of two vectors, cb multiplied by xy, and then we, so zj is the dot product of cb and coefficients in all the variables. Yeah? So coefficients in the cost function dot coefficients in the variables. Okay, and we know what is cj and we know how to subtract them, and we got some values. Okay, so now you go back to the algorithm again. So we completed step 5, we finished step 5. So now we have to go into step 6, identify something called as entering variable. So this is a new jargon. You have to identify something called as the entering variable. So how do you do that? So select the most negative value in the bottommost row, which is nothing but zj minus cj, isn't it? So select the most negative value, and then the corresponding column indicates the entering variable. So which mean, what do you mean by that? This is the variable that will increase the objective function the fastest according to the algorithm. Yeah? So how to visualize this? So select the most negative value. Let's do that one by one. So the most negative value in this row, so in this row, which is zj minus cj, is minus 5. So, and then the corresponding variable, so that's what we say here, isn't it? So once I identify the most negative value, the corresponding column indicates the entering variable. So the corresponding column is this one, isn't it? So this one, this is the corresponding column, and the corresponding variable of that column is x1. So which means x1 is our entering variable. So let's write it. So x1 is the entering variable. So we did identified something called as the entering variable. So we will try to increase this value so that our we'll try to increase x1 so that our profit will increase. So once you have the entering variable, you have to identify. So go to the step 7. So we already completed step 6. We have to go to step 7. We have to identify something called as the leaving variable. So to identify the leaving variable, we have to do something called as the minimum ratio test. So how do you identify the leaving variable? So we know x1 becomes the entering variable. So we have to identify the leaving variable. Yeah? So So to identify the so-called leaving variable, you have to calculate something called as the right hand side and then the coefficient of the entering variable. What do we mean by that? So right hand side is simple. Right hand side is this one, 2, 10, 12. So these are the right hand side of all the constraints, the linear equations, okay, in the constraints. I mean, that corresponds to the constraints. So this is nothing but your right hand side divided by coefficient of the entering variable. So what do I mean by that? So now we know that entering variable is x1, isn't it? Follow, look at the pen name. So x1 is the entering variable. So we need to find the corresponding coefficients. So that's what it means. So you have to take the ratio of right hand side divided by the coefficient of the entering variable. So which means right hand side divided by the coefficient of the entering variable, which is this one. So let's do that here. So RHS by coefficient of the entering variable. Okay, so RHS is what? 2 divided by coefficient of entering variable is 1. That makes it 2. And then right hand side for the second constraint is 10 divided by the coefficient of the entering variable, which is x1, and the corresponding coefficient is 5. 10 divided by 5, that's equal to 2. And then the last one, the right hand side is 12 divided by the corresponding coefficient of the entering variable, which is 3, 12 by 3. So this is equal to 4. So now we calculated the right hand side divided by the coefficients of the entering variable, okay, the ratio. And now we have to select something, the smallest non-negative ratio. It should be non-negative, it should be a positive quantity, and that should be the smallest number among the positive quantities, okay. So that corresponding row indicates the so-called leaving variable. So now let's do that. So out of this, let me underline. So you have three numbers, 4, 2 and 2. So which one is the minimum? So 2 is the minimum. No? If you have two minimum values, then it's typically select the one in the topmost row. So which means 2. So this is the minimum value and it is a positive quantity when you compare to 4. So the corresponding row, that becomes the leaving variable. So that's what it states. So the row that gives the minimum ratio indicates the leaving variable. Okay. So now, so this is the minimum value 2, and the corresponding row is here, and the corresponding variable in that row is x3. So x3 becomes the leaving variable. So x3 is the x3 is the leaving variable. So let's do that. So we almost still we are not almost there. We have to do a lot of things. So once you identify the leaving variable, we already identified the entering variable. We identified the leaving variable. So now we have to identify something called as the pivot element, or sometimes called as the key element. So what is this pivot element? Pivot element is the value in the intersection of the entering column. So in our case, that is x1, and the leaving row. In our case, that corresponds to the row where you have the variable x3. So we have to identify the pivot element. So pivot element is the point of intersection of the entering column. So which is this column that corresponds to the entering variable x1, and then the point of intersection of the row that corresponds to the leaving variable. So leaving variable is x3. So this one and this one. So which point? Where is the point of intersection? So point of intersection is here, isn't it? So this one. So that becomes your pivot element. So that's your pivot element. So we almost completed step 7. So once identified, pivot element. So we have to go to the steps 8. Yeah? So we have to perform few operations. These are called the pivot operation. Yeah? So we're going to perform a series of operations. They all can be, in general, we can call the series of operations that we are going to perform now as something called as the pivot operation. To perform this pivot operation, you should know what is your pivot element, which is something that we already identified, isn't it? Yeah? Using the set of protocols that we learned until this point. So let's do step 8. So perform the pivot operation. So to do that, you have to create the new table, new simplex table. So let's do that. Let's do the new simplex table. So the procedure is same. We have to have all these quantities in top of the simplex table. So CB, XB, RHS right hand side, and then X1, X2, X3, X4, and X5. And then write a cost function as well, just for reference. 5x1 plus 3x2 plus 0x3 plus 0x4 plus 0x5. So let's fill in the simplex table, but now we have to follow a few rules. So what are the rules that we should follow? So we identified something called as the entering variable, and we also identify something called as the leaving variable. We identify the leaving variable and the entering variable for a reason, isn't it? Yeah? So what's the reason is? So that's, we need to know what's the entering variable and what's the leaving variable to build our next simplex table. Yeah? So let's build that. So we know x1, x3 is going to be the leaving variable, and x1 is going to be the entering variable, isn't it? Yeah? So now we construct the new one. So I will show how to construct. So everything is going to be the same, but so x3 will be leaving from this table and x1 will be replaced. I mean x1 will replace x3. So let's write that one. So we're going to kick x3 and then replace it with x1 because x1 is the entering variable, and then the remaining things will remain same, x4, x5, and cb. So this is the coefficient of all variables in the cost function, isn't it? Yeah? So which means the corresponding coefficient of x1 in the cost function is 5. You also enter that value 5, and then the corresponding coefficient of the x4 and x5 in the cost function is 0 and 0, isn't it? Yeah? So enter that value 0 and 0. So this value will not change. Yeah? So it's just write your right hand side equation, which is 2, 10, and 12. So no change in this column, 2, 10, and 12. So the right hand side will not change. And now here you have to pay attention. So this is something called as the pivot operation. Yeah? So what do I mean by that? So for the moment, let's write this all the coefficients here: 1, 1, 1, 0, 0, 1, 1, 1, 0, and 0. So now you have your pivot element. Your pivot element is here 1. Since your pivot element is 1, you have no issues. And if you go back to the rules, the rule book, you have to, so as part of the pivot operation, you are supposed to normalize the pivot row. So we have to divide the entire row by the pivot element so that the pivot element will become 1. So if this value is 3, for example, if this value is 3, then we have to normalize everything, including the right hand side. Yeah? All the elements in this table by 3. So it will be 1 by 3, 1 by 3, 0 by 3, 0 by 3, and 2 by 3, and 3 by 3. So that makes the pivot element 1. So that way we will normalize the pivot element, so that the pivot element will be equal to 1. So at the moment we already have 1, so which means we don't have to do anything. But in case if this is your pivot element and that pivot element is equal to 3 or 4, then you have to divide the entire row starting from right hand side to all the coefficients in the variables by the corresponding value of the pivot element, so that the pivot element will become 1. So that's the meaning of normalizing the pivot row. Okay, so now we don't have to do all these things because we already know that our pivot element is 1, so which means we don't have to take any further action. So that's all. And now go back to the rule book. So eliminate all other coefficients in the pivot column. So you have to perform some row operation so that all the other coefficients in the pivot columns can be eliminated. So eliminated means, so this is your pivot column x1, because your pivot element is here. So you have to eliminate all the coefficients here. That means this number should become 0. So this is your pivot column. So you have to eliminate all the coefficients in the pivot column. So you have to perform some row operation so that this one will become 0. Okay, so how do you do that? So for the moment, let's label this one as R2, row 2, and this is R3, the first row as R1. So in order to eliminate this element in the pivot column, what can we do? So we can multiply 5 times, R2 minus 5 times the R1. So that should eliminate this number, isn't it? So let's do that. So what I'm going to do now is 5 times, R2 minus 5 R1. So I'm just performing some row operation. So in order to make or eliminate this coefficient in the pivot column, so and you have to perform this operation starting from right hand side. So which means 10 minus 5 into 10, 5 into 2, sorry, and here you have 5 minus 5 into 1. 5 into 1. 1 is the coefficient in the row 1. And here is 2 minus, here you have 1. So minus 5 into 1. And here you have 0, x3, minus 5 into 1. And here you have 1 minus 5 into 0. And you have 0 minus 5 into 0 in the row 1. So that will be, this will be equal to 10 minus 10, 0, 5 minus 5, 0, 2 minus 5, minus 3, 0 minus 5, minus 5, 1 minus 0, 1, and 0 minus 0, 0. So take a note of these values: 0, 0, minus 3, minus 5, 1, 0. So somehow we managed to eliminate the coefficient in the pivot column, isn't it? So we have to eliminate all the other coefficients, excluding the pivot element, because pivot element we try to normalize, which means your pivot element will be equal to 1 after normalization, and we have to eliminate all the columns, all the coefficients in the pivot column. So by performing some row operations, that's what we did. So now perform the same here. So how do you eliminate 3 from this row, from this column, sorry. So this, we have to eliminate this coefficient, 3, because this is your pivot column. So we can take row 3 minus 3 times R1. So that should eliminate this coefficient, isn't it? So, and you have to perform this operation starting from RHS. So that's 12 minus, so we are going to do R3 minus 3 times R1. So 12 minus 3 times 2, and here 3 minus 3 times 1, and then 8 minus 3 times 1, and then 0 minus 3 times 1, and then again 0 minus 3 times 0, and then again 1 minus 3 times 0. So this means this should be equal to 12 minus 6, that's 6, and 3 minus 3 0, 8 minus 3 5, 0 minus 3 minus 3, and then 0 minus 0 0, 1 minus 3, or 1 minus 0 1. So if you look at the table here, so you managed to eliminate the coefficient in the row 3, yeah, with respect to the pivot column. Yeah. So what do I mean by that? So we eliminated all the coefficients in the pivot column excluding the pivot element. Yeah. So this becomes 0, this becomes 0, and your pivot element is 1. Almost done, 50%. Now we have to write the same thing. So go back to your previous table. So we need to write again Zj, Cj, and Zj minus Cj. So Zj is, we have to recalculate now based on the coefficients here. Yeah. So now the coefficients in all the columns changed, isn't it? Yeah. And so does the your Cb values as well. So now we have to calculate Zj, which is Cb dot x of I, isn't it? Yeah. So let's calculate it. So you got to multiply Cb multiplied by x1, Cb multiplied by x2, Cb multiplied by x3, Cb multiplied by x4, and Cb multiplied by x5. So let's do that. So 5 multiplied by 1 plus 0 multiplied by 0 plus 0 multiplied by 0. So 5 multiplied by 1 plus 0 multiplied by 0 plus 0 multiplied by 0. And then do the same for the next column. 5 multiplied by 1 plus 0 multiplied by minus 3 plus 0 multiplied by 5. Do the same. 5 multiplied by 1 plus 0 multiplied by minus 5 plus 0 multiplied by minus 3. And then do the same. 5 multiplied by 0 plus 0 multiplied by 1 plus 0 multiplied by 0. And do the same here. 5 multiplied by 0 plus 0 multiplied by 0 plus 0 multiplied by 1. So what's this value? So 5, this makes it 5, isn't it? Yeah, 5. And then equal to, this is again, this is again 5, isn't it? Yeah, and this one is 5 plus 0 plus 0, that makes it 5. And this one is 0 plus 0 plus 0, 0. Again 0 plus 0 plus 0, that makes it 0. So Zj minus, this is Zj, no? This is the updated Zj value. So now we have to calculate, write the Cj value. So Cj is nothing but the coefficients of the variables in the cost function, so which is going to be the same, no? 5, 3, 0, 0, and 0. 5, 3, 0, 0, and 0. So now we have to calculate same Zj minus Cj. So Zj minus Cj, 5 minus 5, 0, 5 minus 3, 5 minus 0, 5, 0 minus 0, 0, 0 minus 0, 0. So this is a good news because everything in this row Zj minus Cj all are positive quantities, isn't it? So this is a must condition. So once you identified or once you realize that Zj minus Cj is all the quantities in this row is a positive, then which means we can stop the iterative calculations that we are supposed to perform, and then which means the problem is almost converged. So everything is positive. So now we have to write the conditions. So for maximization problems, Zj minus Cj, I mean in the row, all the values in the row Zj minus Cj, all the values should be positive. So that means we already identified some conditions where your profit will be maximum, which means Zj minus Cj should be greater than or equal to 0. So this is the main criteria in the simplex algorithm for maximization problem. So now we have to write the cost functions. So we have to rewrite, or we need to write, not rewrite, we need to write the cost function based on the xb, note this one, xb and the basic variables, b value in the simplex table, or we can call it right hand side, xb and the right hand side value in the simplex table. So what do I mean by that? So let's go back to our the rule book. So continue the simplex iteration. So this is, we already recomputed the Zj and Zj minus Cj, and we are supposed to continue the simplex iterations as long as any value in Zj minus Cj is negative. So before, in the first table, we found this value is negative, isn't it? So which means we have to construct another simplex table, but in our case, the second simplex table that we constructed right now, all the values in Zj minus Cj is positive, isn't it? So which means we don't have to continue with the simplex iterations, rather we stop, and then the process stops when everything is positive. This is something we already reached. Zj minus Cj now is greater than or equal to 0 for all the columns, isn't it? And then, so the basic variable xb and their right hand side value, that gives the optimum value for x1 and x2. So what do I mean by that? So in this case, whatever the basic variable that you have here, we have x1, x4, x5, and reminding, if you remember that when I start to explain the problem, I said x4 and x5, these are some unused resources. So this will never come into their actual cost function. So we are using this to implement the algorithm. So at the moment, we have only x1 and the corresponding right hand side equation. So this should this already tells something about when your profit will be maximum. So take a note, xb and the right hand side. So that's what I mean. The basic variable and their RHS value give the optimum values of the decision variables. So in this case, the decision variables we have is only x1. So which means x1 should be equal to 2. So what do I mean by that? So your profit will be maximum, your Z will be maximum when x1 is equal to 2. So which means you write the profit function, the original profit function, 3x2. So Z will be maximum when x1 will be equal to 2. And in this table, you don't have x2, isn't it? You have only x1. So this means x2 is automatically equal to 0. Suppose in this table, if you have x2 and some values on this side, then you have to include that value as well. Yeah. So then you have to include x1 is equal to 2, and imagine you have x2 here and you have some value, say 2 or 3, then x2 will be equal to 3, and in that case z will be maximum when x1 is equal to so and x2 is equal to so. Yeah. So in our case x2 is equal to 0, so which means your profit will be maximum when x1 is equal to 2. So that completes the simplex algorithm. So actually what we did is we tried to solve a LPP problem, which is actually a chemical engineering problem converted into an LPP problem. Maybe I will make a separate video and I will try to explain how this chemical engineering problem is converted into an LPP problem. So that's the LPP problem. Yeah? Linear programming problem. Yes. So thanks for listening.